There are many forces we will deal with over and over. In this video, I will introduce you to some of them and to the symbols we use to represent them. Let's start with the force of weight, known as weight. A falling rock is pulled towards the air by a long-range force of gravity. Gravity is what keeps you in your chair, keeps the planets in their orbits around the sun, and shapes the large-scale structure of the universe. We will have a thorough look at gravity later. For now, we will concentrate on objects on or near the surface of the Earth or other planet. The gravitational pull of the Earth on an object on or near the surface of the Earth is called weight. The symbol of weight is usually lowercase w, because uppercase W is actually occupied for another quantity, and it has an arrow. Sometimes some books like to put this as a force of gravity, but we will use this FG for another case when we discuss the gravitational force in a larger scale between the planets and in a solar system. Now we will deal only with the weight as a long-range force. Later in further concepts, when we learn about electricity and magnetism, we will talk about electric and magnetic force that are also long-range forces. But for now, let's limit ourselves with the weight. Well, the agent for the weight force is the entire Earth pulling on an object. The weight force is in some ways the simplest force we will study. An object's weight vector always points vertically downwards, no matter how the object is moving. Let's take a look at situations when you have let's say a ball thrown upwards and a ball is falling downwards, and ball that is rolling on the ground, okay, and let's say a ball that is being shot into a basket in a projectile motion, let's say, right? And I'm gonna show you also the path that they're taking. And it's not a vector, it's just a path that I'm showing. And here's how it goes. Let's say a ball that is at rest. The weight for all of these cases could be would be directed downwards. Let's draw for each ball the particle, represented as a particle. I'm just drawing it next to it so you can see particle and particle. And the weight for all of them will be downwards, no matter where it is going. The weight is always downwards because it's the Earth that is pulling it down. So I strongly suggest you to put this little thing showing that this is lowercase w, because it is easy to confuse with the notations. We often refer to the weight of an object. So this is an informal expression of force weight, the magnitude of the weight force exerted on the object. Note that the weight is not the same thing as the mass. So weight and a mass are different, and I will explain these differences in a separate video. The next force I want to discuss is called a normal force. This force that is present is a constant force that is present when we have an object resting on a surface. So, and it is a contact force, as I said. So suppose that we have an object that is sitting on a surface. Here's the surface. And here we have an object. So when an object rests on a surface, there is always a component of force perpendicular to the surface, and as if the surface is pushing the object upwards, perpendicular. Okay, so we denote this as a lowercase n. In some cases, they use uppercase normal force. It really doesn't matter. It depends on the book. And if we want to represent it as a particle, so we put a dot and the normal force upwards. Well, it is normal force is always perpendicular to the surface. So let's write that for you. Normal force is always perpendicular to the surface. For example, if you have a surface that is inclined, and let's say the object is sitting at an incline right here. So the normal force, according to its definition, it has to be perpendicular to the surface. So it has to make this 90 degrees normal force. Okay, so if you want to draw this object right here, that would be the dot and a normal force going perpendicular to the surface. Okay, now in the first picture, the object resting on a surface, it's not only the normal force, but it's also the Earth's gravitational force, which is the weight of that object, is also acting on it. So I'm going to put the weight downwards here. Okay. In the second case, well, remember the weight is always going downwards, so vertically downwards. That's how the weight is going to be represented. Well, the word normal refers to the fact that this force always points away from the surface. There may also be a component of force parallel to the surface, and we call that as a friction force. You have certainly observed that a rolling or sliding object, if not pushed or propelled, slows down and eventually stops. You have probably discovered that you can slide better across an ice than across an asphalt. And you also know that most objects stay in place on a table without sliding off, even if the table is tilted a bit. This force, the force that is responsible for this sort of behavior, is the friction. And the symbol for friction is, as I said earlier, it's a lowercase f, okay? Because it's a very, very special force. Friction, like the normal force, is exerted by a surface. Unlike the normal force, however, the friction force is always parallel to the surface. So if we again draw a surface and an object that is moving or even stationary on a surface, let's say you have an object that is experiencing a already we know two forces, its weight. I'm just gonna put my little particle, define the object as a particle or represent the box as a particle. And so we already know the two forces, the weight of the object, the normal force of the object, which is perpendicular to the surface, and the friction that is parallel to the surface. Let me write that down. Friction parallel to the surface. So if the object is moving, let's say to the right, or is about to move to the right, it's stationary, but if you take away, like if you put it on the ice, it would certainly move to the right. So then the friction will be always going to the opposite direction to its motion. So the friction is going this way, parallel to the surface. In reality, what is happening with the friction? How does it work? So the surface, it pretty much depends how the object and the surface are interacting with each other. So if you take let's say the surface and look microscopically, the surface might have this kind of not very smooth smooth surface, right? It's not very smooth. In reality, there are no smooth surfaces. Ice is the closest smooth you could find, or maybe, I don't know, you could make some materials to be very smooth. Similarly, if you take the box, right, the bottom of the box is also not as very smooth. When the box is sitting on the surface, in this area, you have a kind of a reflection from the surface and the box, as if these uneven surfaces do not allow each other to move unless there is a force that is overcoming. You can push through this, okay? Otherwise, it will keep staying stationary because that force is keeping there. Now, the similar explanation could be done for the normal force. What is the surface made of? You can think of this one. If you have a box on a surface, in the previous case, somewhere, where is it? Let's say we're looking at this example, right? The surface itself, you can think of molecules. Imagine, okay, so think of the molecules that are kind of bonded with each other, and these bonds could be represented as springs, okay, like this. So when you put the box on the top, what happens? These springs stretch. Okay. Now the box goes, or the block goes on the top. What happens to the spring? The springs actually start stretching, okay, and this point goes in here. Think of this way. So the spring wants always this other spring is actually gets compressed here. So, and this spring is going to push back the box as if it wants to come back to its original position. So these little pushes of these imaginative springs make a normal force. So that's how the surface pushes it up. Now, going back to our friction, we can say because of the friction depends on the smoothness or the roughness of the surface, we could say that the rougher the surface is, the more these atoms are forced into close proximity, and as a result, the larger is the friction force. Yeah, the atoms that I'm talking about is when in a microscopic level, when you look, friction arises as atoms from the object, and atoms on the surface run into each other. That's what I meant with the atoms. So there are two types of friction, and two kinds of friction. One is called kinetic friction, another one is called static friction. So kinetic friction is denoted with a lowercase f and a little subscript k in there, and acts as an object slides across the surface. So the word kinetic means moving, okay, it's motion. So kinetic friction is a force that always opposes the motion, meaning that the friction force on a sliding object points in the direction opposite the direction of the object's motion, as if the friction doesn't want the object to move. It's just the resists the motion. Another kind of a frictional force is known as a static force, and it is denoted as lowercase f and s next to it. So this is static friction. Let me write on the top that it is kinetic friction that we talked earlier. And then static friction is the force that keeps an object stuck on a surface. The word static comes from the word stationary, so it is static. So this force, as I said, it keeps an object stuck on a surface and prevents its motion relative to the surface. Finding the direction of the static force is a little bit trickier than finding the direction of the kinetic force. So static friction points opposite to the direction in which the object would move if there were no friction. That is, it points in the direction necessary to prevent the motion. The next force I want to discuss is the tension force. When a string or rope or wire pulls on an object, it exerts a contact force that we call a tension force. And it is represented by a capital letter T. Okay. Watch out, we will use this capital letter T for another quantity. But for this moment, we're using capital letter T because we don't want to confuse with the time, which is a lowercase t. So be careful with the notations. Well, the direction of the tension force is always in the direction of the string or rope, as I can show you in a picture. Here, the rope exerts a tension force on the object, on the box. So if I were to draw the box as a particle, then the force of the tension would be in the direction of the rope, and I would call it tension here. Now let's, if we try to draw other forces that we learned, obviously this rope this box will be moving to the right, hopefully, if the rope is pulling with enough force. So the forces that act on it would be the weight that is always downwards. It would be the normal force that is always perpendicular to the surface, and it would be the friction that this surface is actually exerting. Because the box is moving to the right, the force between the friction between the surfaces of the box and the surface that it is moving will be on the surface. So this would be the friction, and then normal force will be pushing the surface, will be pushing the box up, and then there would be the earth that is pulling this guy the box downwards. It's the weight, and the rope that is pulling it towards it. As you can see, this is a very complicated picture I drew. Well, when you draw with the particle and all the forces starting from it, our friction force that I need to draw to the left, and that will be my kinetic friction, and let's not forget the vector. So then I would have a simpler picture drawn in here rather than having a big one. So this is called free body diagram. I'll make another video on that separately. So we can also think about the tension force using some kind of a microscopic picture. So if you were to use a very powerful microscope to look inside the rope, you could see that it's made of atoms joined together by molecular bonds. So these blue dark dots are the atoms, and the spring type of things are the molecular bonds. So these molecular bonds are not rigid, and they can actually be looked as springs holding the atoms together. Pulling on the ends of the string or rope stretches the molecular springs ever so slightly. So for example, if you're pulling this string or the rope, so these molecules are being pulled, the atoms are being pulled this direction, and so the other end is being pulled the other direction. So what you end up having, these bonds actually get stretched. The more you stretch, the more tension you get. If you stretch too much, you might even break it. So we'll talk about this later in a different, when we discuss different concepts. You might also say these forces I drew on the ends, but the tension within a rope and the tension force exerted by any object at the end of the rope are really the net spring force exerted by the billions and billions of microscopic springs. So if you have a rope, then the tension everywhere in this rope should be the same. So the tension here is the same as the tension on this on the rope in here on the other side, or here, anywhere you take, the tension is the same because of its the tension is the net spring force, the total superposed spring force of the billions and billions of microscopic springs. I'll talk next about the spring force. The atomic level view of the tension introduces a new idea, a microscopic atomic model for understanding the behavior and properties of microscopic objects. We we will frequently use atomic models to obtain a deeper understanding of our observations, as I did it for friction and I did a normal force. The atomic model of tension also helps to explain one of the basic properties of the ropes and the strings. When you pull on a rope tied to heavy box, the rope in turn exerts a tension force on the box. If you pull harder, the tension force on the box becomes greater. How does the box know that you are pulling harder on the other end of the rope? According to our atomic model, when you pull harder on the rope, its microscopic springs stretch a bit more, increasing the spring force they exert on each other and on the box they are attached to. Now, let's talk about the spring force. I keep referring to it. So it's known as a spring force. Which is denoted as F and subscript SP for spring. Okay, what happens when you have spring that is attached to a wall on one end, and it is also attached to a box on the other end, and let's suppose that this box is sitting on a surface. Okay. Well, if we push this box towards the wall and let it go, so the box is going to come back to its original position or move forward to the right, because of the spring is going to push it forward. So if the box is moving to the right, that you can say the spring is the one that is pushing. Now, to draw the force, we'll just make the box as a particle, and then the force is towards the direction of the motion. So F, spring. Now, what happens if you pull the box further, okay, with the spring? You will stretch the spring, let's say, to its furthest distance, and the box is sitting here again, and then you let it go. What's going to happen? Your box is gonna move to the left. When it moves to the left, then the spring is the one that wants the box to come back, because spring doesn't want to stay stretched or compressed. So it does want to come to its original position. So therefore, the spring force will be directed to the left, to this direction. Let me draw it for you. F spring. Now, the object that is with the spring in general has already several forces on it. How would I draw this? The object is on a surface, and let's say surface has some roughness, so there is a friction force, and it is on a surface. Let me draw it a separate picture. So here's my object, the box, okay? The object is on the earth, so it is experiencing a weight. We always draw weight downwards. Also, the surface is pushing the object upwards, so there is a normal force going perpendicular to the surface. And then there is a friction on the first case. This is my first case, where the object is moving to the right, then the friction force is opposite to the motion, and it is a kinetic friction because the object is moving. So I'm going to draw the kinetic friction going this direction. Okay, and then finally there is a spring that is pushing forward, so this would be spring force going to the right. This would be all the forces acting on the object. Now, in the second case, the picture is a little bit different. Let's take a look. First of all, we have the object that is a particle dot. So the weight is still the same because Earth and a box have the same relationship with each other. So here's the weight. And the surface is always pushing perpendicular upwards, so normal force up. And then we have the spring force. The spring is pulling object to the left, okay? And this time, because the object is moving to the left, friction is going to the right. So then friction force will go to the right, kinetic friction. One more force, or apparently two more force that I want to discuss with you is the drag force. In previous examples we have been, when we were solving projectile motion, we always said let's ignore the air resistance, air drag. So that's a drag force, okay, which is also a frictional force. So let's say if you have a, let me just write the name of it first. And then let's consider, let's say a leaf, okay? A leaf that is falling from a tree. Okay, so let me draw just a kind of a leaf. So a leaf is falling. What is happening? First of all, a leaf is falling downwards. Why? Because it has a weight and the earth is pulling down. But there is also an air. We don't have an emptiness, although you don't see it, but there is an air. So what's going to happen? Air is going to keep the leaf from falling. So it's going to resist the falling of the leaf. So speaking with the language of physics, we would say resistive forces are experienced by objects moving through fluids. Fluids are gases like air and liquids like water. Like if you throw, let's say, some object into honey, it will take a little bit longer to go down because there is a resistive force. The honey will just resist its fall. So this kind of resistive force, the force of a fluid on a moving object, is called a drag, and will be symbolized as, in some books they put like a D, or they just write FD, like a drag force, but mostly they use a D as a drag force. So the air drags the leaf. And this is like kinetic friction. Drag points opposite to the direction of motion. So in other words, if the leaf is moving downwards, the drag force is going to push the leaf up, like as if the air is opposing it. So if I want to draw this in a particle model format, so this is the particle that is falling, and here we have a drag force going upwards. Yes, if you're interested, we can also draw the weight of the leaf. Okay, so the weight. Obviously, the weight is larger than the drag force. That's why eventually the leaf falls. We will discuss this a little bit in deeper version how to calculate the drag force later in a different video. Drag can be a large force for objects moving at a high speed or in dense fluids. On the other hand, for objects that are heavy and compact, moving in air and with a speed that is not too great, the drag force of air resistance is fairly small. To keep things as simple as possible, we can neglect air resistance in all problems unless a problem explicitly asks you to include it. So the error introduced in the calculation by approximations is generally pretty small. The next force we want to talk about is thrust. A jet airplane obviously has a force that propels it forward. Likewise, for rockets, the force that is called thrust occurs when a jet or a rocket engine expels gas molecules at a high speed. So the thrust force is exerted on a rocket by exhaust force. So if we imagine the rocket to be this particle, then a thrust force is the one that pushes the rocket forward. So this is force of thrust. Thrust is a contact force with an exhaust gas being the agent that pushes on the engine. The process by which thrust is generated is rather subtle and requires an appreciation of Newton's third law, which I'll talk about later. For now, we need only to consider that thrust is a force opposite the direction in which the exhaust gas is expelled. There is no special symbol for a thrust force, so we can call it F thrust, like that. So the gas will go downwards. The rocket will go upwards because of the molecules of the gas, exhaust gas is going to push the rocket upwards. And the other two forces that we would talk in later videos, that's the electric and magnetic forces. Electric and magnetic forces like gravity exert forces on a long range. The forces of electricity and magnetism act on a charged particles. We will study this later after we understand the dynamics. It will come to us when we study electricity and magnetism. So that's for these are the main forces that we will be dealing in this course. Let's quickly summarize what we have learned, how many forces we have learned in a small table. So let's put on one side forces, the other side notations, because sometimes they're important. So general force, we just denote with a capital letter F. And weight, we denote with a lowercase w. Sometimes in some books you might see Fg, like force of gravity. Spring force, as F spring. Tension with a capital letter T. Normal force, either capital letter N or lowercase n. Static friction, that is Fs. Kinetic friction, that is Fk, lowercase f, and drag force with a capital letter D, and a thrust as F thrust. And finally, remember, when you want to identify a force, you need to identify what is the agent and the object. So for the force, you need agent and object to be exerted on. Thanks for watching. Stay tuned for more to come.